Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you're watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody.
Hello, welcome.
All right. Well, welcome to another episode of Ask Us Anything About Electrochemistry. We got the boilerplate stuff out of the way, and we got some questions coming in. So I guess we'll just start things off.
We'll just get right to it. It feels weird, you know. For like a year, we spent doing these. I got to sit here quietly while you did all the boilerplate stuff, and then you recorded yourself doing the boilerplate stuff. So now it's like we just have to start answering questions.
We just go.
It feels weird, honestly.
But we can still like say hello to everybody, and just to remind you that it's not just a pre-recorded video of that information.
Yes.
We are still here doing these live.
Yes, we are.
But I don't have to memorize all the boilerplate stuff and say it again.
It must be a load off for you, especially for me. Whenever you weren't here and I had to do them, I was always like, "Oh God, Alex does these. I don't remember."
Yeah.
I'm like, ask questions and I don't know your name and something about
it on a Word doc that lives on my computer, like desktop.
I know, but you don't want to be like reading it. You know what I mean? You want to kind of, obviously, the art of video.
Exactly.
Live streaming and whatnot. So welcome everybody. It's good to see you. Good to see you, Chris.
Yes. Yeah. Good to see you too, Chris.
So
there's a question. We're just gonna go these by the order that they come in through either LinkedIn, Twitter, X, or YouTube. We have a question from Sudeep Sagar. He says, "Currently, I am pursuing a master's in energy technologies, battery technology. Could you help me? What are the best areas to work on for my thesis? It's a research project. This is a master's, basically in battery science. I may default to you on what you may think is a good topic to do.
It's a good question, but honestly, I it seems to me like your question is what sub topic is best, because you sort of already answered your question. If you're saying where should I pursue my research topic, you're doing battery technology, I assume. So I'm not trying to be glib or anything. I'm just so battery technology or batteries sort of in general is obviously a tremendously relevant and useful field, because battery technology and rechargeable batteries in particular, of course, are so ubiquitous and only growing in their need in terms of consumer electronics and even stationary energy storage to a certain extent. It's I guess what I would say is, from my personal experience, I worked on batteries as a PhD and in my postdoc, and I studied anodes for a variety of reasons. I won't talk endlessly about that, but I studied anodes. I found it really fascinating. I love batteries. It's one of the reasons I really enjoyed my PhD and my postdoc. Batteries fascinate me just sort of in general. And I studied the anode, and then I also studied full cells. I studied like failure mechanisms and different things. So there's a lot of places for you to study. I guess in some very general sense, and from a technical and thermodynamic perspective, or I guess kinetic from a scientific perspective, let's just say, the cathode is the limiting part of a battery, technically speaking. It's the same with a fuel cell. It's the limiting one. So the cathode has a lower specific capacity than the anode. The cathode tends to have to be thicker than the anode to make up for its smaller capacity. And so in some very real in some very real way, let's just say, if you're trying to think about what has the most practical impact, the cathode, and then maybe other tangible aspects of a battery, for example, the membrane or the electrolyte, which are, you know, important parts of it too, could be studied. But the cathode is something that is the limiting thing. So basically, it's like you can make an anode so much better, but it won't matter necessarily because the cathode's already the limiting side. Now, that doesn't mean that other parts of the battery aren't worth studying. And particularly, of course, from an academic perspective, you're not always concerned about what I'm researching needs to become, the state of the art technology tomorrow. There is value in, however you want to say it, research or study for its own sake. That is one of the values or purposes of academia, and a research project like this. So that's not to discourage you from studying something like the anode, which, again, as I said, in some practical sense is not as needed, like for a marketable technology, but still useful to study, and you'll learn a tremendous amount. That's exactly what I studied. And then, Chris actually points out one of the big issues of battery technology isn't electrochemical, it's failure mechanisms and thermal runaway. I studied exactly that in my postdoc, actually. So I started studying anodes, which, as I said, are useless. That's not what I meant. But I started studying anodes. I learned a lot about batteries and battery mechanism and all kinds of different things. And then I studied failure mechanisms, thermal runaway, heat propagation, failure events, and how to sort of either quantify them, as well as predict them, diagnostics techniques and things like that. So that's a trickier kind of a topic to study. It depends on where you're studying, of course, right? So not every institution may have the capability. For instance, in the United States, Sandia National Lab is one that comes to mind. In New Mexico, I think, right? Sandia's in New Mexico. I think that's correct.
I think so.
Yeah, it's in Albuquerque.
Yeah.
I've been there, so I should probably know that like a lot more quickly than I am trying to remember. It was many years ago, but I visited there, and they have a tremendous facility where they blow up batteries and study what happens. I did that too at a different facility, but just as an example, not everywhere is Sandia, and not everywhere has the capability to do that. So, to Chris's point, that's a good thing to study. The unfortunate reality is that it's not everywhere that has the ability to like blow up batteries and find out what happens, or see how thermal runaway occurs. It's tremendously destructive, right? It releases a lot of gas and toxic fumes and stuff. So you have to have a special kind of setup to study something like that. So in the absence of that, if you're looking at a particular kind of topic, the simplest thing is study the anode or the cathode or the electrolyte. And so you're just going to be formulating different materials, different morphologies, different materials characterization kinds of things, and seeing how it impacts battery capacity, battery conductivity, battery longevity, different things like that. Those are all very useful things. And as I said, at the very least, you should probably gain for yourself a good grasp and understanding of batteries in general, which will carry you, hopefully into your professional career. If you stay if you go into industry, for instance, some research in almost any part of a battery, study, anode, cathode, whatever, will help guide you if you want to do batteries, for instance, of an industrial, scale, or at a job. That will really help propel you that way.
Yeah, I think the only 2 cents I'd add is I hear a lot of people also they could study the SEI. They could make electrolytes.
Yeah,
that's always another thing. Like, so if you're interested in synthesis of like new materials, new electrolytes, things like that, that's another. Just different battery materials. So those are the other areas I've at least heard about. Thank you all for your comments. Thank you, Shruti. We like to think we have a pretty good YouTube channel. Trying to make it hopefully the best. We have a question from Mustafa from LinkedIn. Could you please explain in the Dunn method, which is used to determine the ratio of capacitive and diffusive behavior, why, if the power B is equal to 0.5, represents diffusive behavior, and if B is equal to 1, it represents capacitive behavior. Thanks. So it's interesting in my time either learning electrochemistry or looking in this textbook, Bard and Faulkner, the electrochemical methods, fundamentals, and applications. I rarely run across the Dunn method. It does not seem to be a thing that I've at least like experienced or worked with. And but the Dunn method in principle. So I don't know exactly what the B value represents, or at least the equations. So there's no like Wikipedia, or at least I haven't been able to find a Wikipedia article on the Dunn method. But some people still have different like experiments and stuff about it. But all I know, generally speaking, and if I'll just share my screen quickly. So I think, yeah. So like the Dunn method. Hopefully, people are able to see my screen. Yeah. So the Dunn method, and if you just look at this kind of image right here, is the idea that if you take a cyclic voltammogram with, and in my understanding, with and without the analyte, you will be able to observe kind of two voltammograms, both taken at the same sweep rate, and you will be able to assign the fraction of the current that is associated to capacitive behavior, and a fraction of the current that's associated with diffusive behavior. And there are kind of other pictures like that where this is the diffusion limiting current, and this is diffusion or pure capacitance. I don't know enough actually about the B.
There's a very funny
value.
parallel here, though, and I don't have any personal experience with this method either. All I can sort of just almost think out loud or ask the question out loud here is there's a very interesting parallel here. B being 0.5 represents diffusive behavior, and if it's 1, it's a capacitive behavior. What does that remind you of?
Reminds me of impedance spectroscopy.
Yes, I mean, good. I'm glad I'm not alone. Like,
yeah,
I mean,
CPEs, right?
Yeah, this is no. This might just be coincidental. And again, I'm sort of speaking somewhat. Maybe speaking out of turn here, but like a constant phase element. I can pull up. Where am I at here? Let me share. Just as a point. I don't know again if this will be pertinent to the Dunn method, particularly, especially if the Dunn method is apparently a method with what's up?
Oh no, continue.
Okay.
Yeah, everything's good. I hid the
you hid the
question
right,
just so we could see.
If the Dunn method is one of cyclic voltammetry, this is impedance spectroscopy. But for instance, let me just make the resistor really small and kind of illustrate the point here. So this is basically a power function. It's the equation for a constant phase element Q or CPE, right? It's a non-ideal capacitor. The impedance of my CPE is equal to 1 over j omega Q, and j omega is to the alpha power. So it's a power function here. So I'm just sort of pointing this out because it's curious, right? When alpha is 0.5, it's diffusion. When alpha is 1, it's a capacitor. So maybe there's a relationship here. Maybe there isn't. I probably have to look into the Dunn method a little bit. Maybe you can as well. Maybe you can, I don't know. see if there's a correlation or a parallel perhaps between the Dunn method and impedance spectroscopy, or the analysis of capacitive elements or something like that. Seems a little more than coincidental that would be there.
Yeah.
So interesting, just interesting.
Yeah, I think it's just, for me it's strange. The Dunn method, I just don't know. I guess I don't know enough about it. But like, if you have a traditional electrochemical system, just a redox reaction in solution, you don't need the Dunn method to figure out like diffusive versus capacitive behavior. And you don't, but at the same time, you also don't get the same type of behavior. The fact that you have these peaks and these curves that show up when there's no analyte, and then when you add the analyte, you get higher peaks and curves, is a little strange. And perhaps the Dunn method really only works for like, these supercapacitor systems, as I'm reading more about it. But whenever, like, when we simulate cyclic voltammetry responses with simulation, there's no need for like the Dunn method. There's like current that's associated with like diffusion and current associated with capacitance, but it's very clearly like defined. And like the diffusion, like capacitive current only happens when there's a capacitor, and that has a very specific kind of signal. And then there's current associated with diffusion and Faradaic processes, and that's a certain kind of signal. You wouldn't get like a peak and then say that part of the peak current is like capacitive. I guess I'll just draw it this way, in kind of contrast to, I think I'm showing, right.
Yeah. Oh yeah.
Yeah.
Good.
Okay. So if I have a voltammogram, and this is my cyclic voltammogram, I'm just going to kind of exaggerate it a little bit here. But if this is 0, I know that this type of current here is all like capacitive, and that the current, and then like, yes, I can kind of extrapolate this out in time or out in voltage, and so like, oh, this is my actual, there's a background current here that's capacitive, and then there's a Faradaic current here, and that's like diffusive, sort of say diffusion. Let's call it diff, and this is cap. But I would not have a situation where I would ever say that part of this is capacitive. And that's what some of these images, when people use the Dunn method, say. They're saying that part of this signal is capacitive.
Yeah, I think that's a strange conclusion as well, because
Yeah.
the capacitance wouldn't, in theory, change based on potential like that. Which is to your point. Why?
Yeah, you would not get curves like this.
The only way I could say is if there's some material for which that's true for whatever reason. Like, is there a material where its double layer capacitance changes by potential for whatever reason? That seems antithetical, because it's a non-Faradaic process by definition, which means it shouldn't really be potential dependent.
Yeah. So it's I'm just gonna say it's strange. I think it depends on the system, and I think unless you have a very complex electrochemical system, I don't think that method is particularly good. I'm gonna ask Chris very quickly. So Chris said he lost audio.
He said it came back. So
he said it came back.
It's good to check. I mean,
yeah,
we
can check kind of post later whether or not that happens. Okay, all right. So going on. So Mustafa, let us know if you have any further kind of comments about it.
I hear us. Sorry.
You hear us?
I was checking. That's
okay.
Live time checking. So
live time checking.
Yes.
Yeah. So Mustafa, if you're on LinkedIn, if you're still watching, like, please let us know, or you can even send us a message with like PDFs that you're reading that go over the Dunn method, because we don't have access to academic journals, to talk about like this B value when being equal to 0.5 and being equal to 1. So
yeah, I'd want to see the mathematics to know
yeah,
about that, because that's to
and
me,
the
I feel like
system.
there must be a parallel between the constant phase element, which is an interesting thing about it, because I often use the comparison that the CPE is sort of this engineering unit that isn't as based in reality, so to speak. I
Mhm,
mean, it's sort of like adding an exponent to help fit non-ideal heterogeneous sorts of situations.
mhm.
But the reality is that there is some realness to it, for example, at the limits of alpha. And just like this, there might be a power mathematical relationship with the Dunn method of B, where maybe it is also somewhat empirical to fit data, which is that it doesn't represent reality, so to speak, I guess. Right. But at values of 1 or 0.5, it does.
This
So
is an interesting thing, Chris.
maybe
I think Neil, I think you're onto something, because he says it's the purpose is to deconvolute
double layer versus.
electrochemical double layer versus pseudocapacitance.
So it's where if the capacitance does change slightly with potential or something like that, then you would call it pseudo capacitance or something like
Yeah,
that.
and you would change that like alpha value
Yeah.
exactly to
Yeah.
account for it.
Interesting. Yeah, I think there's all some tied up in here somehow, right?
Yeah,
How
yeah,
exactly this works together is interesting.
yeah,
But yeah, I
yeah.
think so.
That's very interesting.
Yeah.
Um,
Well, thanks for the question,
yeah.
Mustafa. I think that's an interesting discussion. That it's fun to kind of talk through some of these things too,
Mhm.
because like we always try to do on these live streams, we're PhD electrochemists,
Yeah.
but we certainly don't know everything about every topic. We do know a decent amount, enough that we hopefully can help you folks answer some questions here and there. But when we don't know about something, we do our
Yeah.
best to acknowledge that we don't know about it. But
Yeah.
I like this format as well, because we get to learn about methods by talking through them and sort
Yeah.
of hearing your perspectives. So it's very helpful
Yeah.
to kind of hear through some of these things.
Yeah. Something to
Yeah, scan rate
research more.
dependent in the CV. Yeah, I mean, pseudocapacitance, of course, is something where like the peak positioning and the height will be scan rate dependent, where it's like in an ideal, perfectly reversible situation, it won't be. For instance, like peak location won't change for a perfectly reversible, but it does for a pseudo reversible or pseudocapacitant. So there's all these sort of pseudo ideal situations, something like
All
that.
right. I guess I can kind of see. I mean, both electrical double layer and Faradaic processes are both scan rate dependent, but I guess you have to do a more thorough
Yeah.
study to elucidate, what potentials, what processes. So, all right, that's interesting. That's very interesting.
Yeah.
We have a question from Shruti. Asked the question again, just kind of going down in order. How do you see the future of sodium ion batteries? I'm working with sodium ion anodes and curious to know just our point of view, which is great, because this doesn't mean that we can be wrong with this question, because it's just an opinion
It
question.
means I'm definitely going to be wrong,
Yeah.
because I studied lithium ion batteries. So, I'll say two things about it. I guess primarily the first is that, I guess not to be so cynical about it, but I know that the bulk of battery research is done with lithium ion technology. It has been for a long time. That being said, there's a lot of folks studying things like lithium sulfur, lithium air, sodium ion, sodium air, zinc, and they're quite popular in certain with certain folks doing those research. Battery research to me is a very strange and funny thing. It feels like the folks who are doing one type of battery research or another are very tribal about their type of battery. So, like, if you talk to folks in the sodium ion battery world, they tend to feel like theirs is the best. It's funny, and so it's almost like it's a fun rivalry in some way, because in another
Like rival sports teams.
yeah, exactly.
Yeah.
It's like sports ball teams,
Ball teams.
which if you have a good rivalry, in theory it can be nasty, but in another way it can make you better, because it's like, no, I'm the best. No, I'm the best, and it's like, well, I'll prove you wrong. I don't know. So zinc folks can be similarly sort of acolyte about their type of battery. So to a certain extent, it's actually hard to answer the question, because it's like I almost feel like it's hard to find sober objective opinions about battery technology, because if you read sodium ion papers, that basically the entire introduction of every one of them is like, lithium ion has been used forever, but it suffers from all of these different things and we should use sodium instead, and it's like lithium batteries papers are like, lithium is the best forever, but there's a couple of things we can still work on, and here's what I'm going to show you. It's like, you don't get there's probably reviews out there that are like fair comparisons, but like I said, the tribalism of the different battery research topics makes it hard to get honest assessments of them. That being said, I think that, as with most energy types of technologies, let's just say more broadly, a non-exclusive approach is best. So a sad answer to your question is something like, the future of sodium ion batteries is bleak because everyone's using lithium ion, and there's a reason why sodium ion isn't in everybody's phone. And some of those reasons are real, like thermodynamic barriers that are just the reality of the periodic table. Like lithium presents more power density, more energy density. Lithium as a metal has a tremendous amount of power and promise and energy density, the whole thing, right? There's a reason why lithium ion batteries are basically everywhere, and they replaced like NiCad batteries before them, or nickel metal hydride before that, or I might have that in the backwards order. But the point is that lithium ion is basically everywhere. That being said, it's like sodium ion has other advantages. It's probably safer. Sodium is a little more ubiquitous, I think, than lithium. It's probably cheaper. Sodium is easier to get, like as a mineral like in the earth, right? Lithium is hard to mine. It's hard to get. It's also, energy intensive, and it's sometimes obtained in ways that are not so nice to humanity. Let's just leave it at that. So there are reasons to pursue other technologies. And then there are situations where perhaps, a less rigorous need for energy or power or whatever is there. You might be able to use something that's slightly, sodium ion. Maybe it's a little safer, a little less energy dense, but can get the job done. So again, as I said, a less exclusive viewpoint is helpful when it comes to batteries or any other energy storage solution. And so I like the idea of sodium and zinc and lithium sulfur and lithium ion and lithium air and all these things being studied to death, because we are going to collectively, like as a research community, find the best options and make them better continually, to improve, energy storage and energy delivery and everything. And that's the whole thing, right? I say this somewhat often when I talk about this kind of thing, but one of the biggest struggles we have, for example, with like phones, right, and computers and cars, is that technology improves faster than battery technology. Just the like, how good is your phone and your camera? You know what I mean?
Yeah.
Like we used to use cameras. Anybody older than 12 remember cameras? Like, have you taken a picture without your phone in the last 20 years? It's like, we've eliminated cameras, except for like, obviously, like film,
certain
obviously.
cameras.
But I'm just saying, like, technology has improved to such a great degree that like your Android or iPhone camera is so phenomenal now. And the applications on your phone and the operating systems are so phenomenally and tremendous. That's like, it requires more energy, and most of the weight and expense in all consumer electronics is because of the battery at this point in time. So like, we desperately need battery technology to continue to advance. So by that logic, like, I'm bullish, I would say, on the future of sodium ion batteries and zinc batteries and lithium. Like, I think that there's a place for all of these. So as a market penetration, I think you don't need to be so discouraged, for example, that there aren't sodium ion batteries everywhere. I think you ought to be encouraged to keep pushing, because we need alternative technologies and we need other ways to sort of supplement the market, for all the reasons I just talked about. So I think you're doing a great thing. I think you need to keep going, and good for you, studying something like this. Keep going. I hope you have great success.
Awesome. Awesome. We have a new YouTube member. Gina Cho became a tier 2 member on our YouTube channel. Thank you so much for joining.
Appreciate it.
We're trying to build a bigger community on our YouTube channel and with Pine Research. And so your membership and contributions help keep our social media efforts very much alive
And thriving.
and thriving. Yes. Yes. So thank you so much. Now we have a question from FCB. FCB, always good to see you with your questions. How to analyze the metal ligand peak by using cyclic voltammetry, and from where we start the cycle and end the cycle. So that's a very good question. I'm just going to make a comment that Chris has already made a few comments. He's saying I'd start looking at like a wide range fairly slowly to find the area of interest. This is with regard to finding the potential window by with which to study your metal ligand peak. And that you may want to actually conduct a blank study on the ligand in electrolyte to determine where it might break down. I actually don't know because like when a ligand is bonded to a metal,
it behaves differently.
It'll behave a little bit differently, and it might just like you may cleave the ligand off. You may still cleave the ligand off no matter what, but it's still helpful at least I think to get some of that data, because that way you'll at least be able to know like, oh, maybe the ligand just by itself actually undergoes an electron transfer. Who knows? So so that's not it's not a bad bit of advice. Generally speaking, and let's just share my screen here. So I am going to be talking about cyclic voltammogram, but if you do have, if you're first off, one thing I'd recommend first, if you have your redox species in your solution, I would measure the open circuit potential. It's the potential with which no current is flowing in your electrochemical cell. It's a very non-destructive technique. So if you're worried about applying the super high potential, cleaving your ligand off your metal complex, just looking at the open circuit potential is very helpful. And so if the open circuit potential is, say, let's say you have like let's just say it's minus 500 millivolts. So I'm just going to put here, just making up some numbers, but it's like, okay, minus 500 millivolts. Well, if you because and your OCP is this, and 0 is here, and this is time. If you start your experiment at say 0, then there's a chance that you may have oxidized your ligand away. So you may actually want to start at a potential close to or near the open circuit potential, or in your experimental parameters, you select a potential 0 volts versus the open circuit potential. And that is just a safe way to determine, okay, what's the potential? Where is your system at? Things like that, without damaging anything. Once you determine this, yeah, I would do exactly what Chris said. I would, look at the voltage versus OCP, and then I would start. Maybe this is 0, and then if you think, I would then try to determine. All right. Well, if you have a metal and you have a ligand, usually your metal will have some kind of redox potential. You can look at a table to determine roughly where is that redox reaction going to be. So maybe it's an oxidation reaction, and so you have to scan positively. So I'd scan slowly, and then I would, you may actually have to do a few scans where like nothing happens. Actually, I'm doing this incorrect compared to the actual IUPAC convention, which we like to pride ourselves on. So this will actually go up a little bit, and then this would go down a little bit. So that may be one experiment, and you don't see anything. But then you do another one, and then like maybe you get like a little bit more current. Actually, this would kind of go up a little bit like so, and then this would go a little bit more like so. But then after maybe your final experiment, if you want to be careful, maybe it's the case that you have to go here, and that's when you get your your duck-shaped voltammogram or something. So it's like once you know that, okay, I can go from here to here and it looks normal. I'm not going like up here and I'm actually breaking down electrolyte all the way in this voltage range. Um, then you kind of can know. But so sometimes you do have to sweep the potential like back and forth, slowly increasing the voltage range while doing your CV experiment. So hopefully that helps you. And let me just make sure I got every part of your question. Yeah, where to start and end the cycle. Yeah, so that's kind of my yeah, so FCB, that's my take on it. Yeah, use a slow scan rate, slowly increment it from the open circuit potential, and that should help you get a good sense of where your redox and your metal ligand charge transfer reaction is occurring. All right.
So Tahira has a question, and
Mhm,
there's a little bit of follow up here, and I'm waiting for the last bit of information. But
mhm,
they say I coated my catalyst on a mesh electrode, used it to run CV. I got 5 cycles when I chose 2 segments, which would be 1 cycle. What could be the reason? So, first of all, I guess Chris was asking were there connectivity issues or something, and then they said that no, the setup is good and the connectivity is good. When I change the number of cycles, the number of cycles changes when I change the scan rate. This does sound like a software problem, and I don't know which
mhm.
program you're using. So if it's Pine software, obviously I can help you more intricately. If it's another company's software, I can help you if I've used it or if I'm familiar with it. I can try certainly. Um, what you are describing sounds precisely like a software issue. If
Mhm.
you put, for example, a CV with 2, you said 5. If you put 2 segments and you're getting 5 cycles, which would be like 10 segments, it's repeating something somehow,
Mhm.
right? Like it's clearly not doing what you told it to do, or it is, but you have checked a box that says repeat n times, like something in the software. Like
Oh yeah.
it just seems like something in the software. It doesn't seem like any possibility that there's a physical issue that would cause it to scan more
Mhm.
than you told it to. It seems like you've either perhaps misunderstood the software um, prompts, or you know what I mean, or
Mhm.
parameter input, or the software is not working properly or something like that. This doesn't sound like an electrode problem. There's the potentiostat's going to do what it's told to do, right, by the software program. And so if the software is not sending the correct signal to the potentiostat, it's a software issue. So anyway, let us know what the software is, and I can try to help if I can.
Mhm.
If it's one of our another company's software, for instance, and we may not be able to help you if we don't, again, it's like I've used a lot of our competitors in my career, so I do know a decent amount about some of our competitors' software, for instance, but I can only help so much, I suppose. But most probably that's what you're doing, and we'll sort of move on while
Mhm.
we wait. And if you have a
Yeah.
follow up on what this other information or what software it is, we'll try to deal with it then. Um, but Mustafa had another question follow up
Mhm.
here. And so he says, I worked in zinc hybrid supercapacitor using a zinc anode and activated carbon cathode. It is clear that increasing the activated carbon surface area will increase the capacity. But what is the effect of increasing the surface area of the zinc anode? Maybe by introducing a nanostructure. Will this maybe affect the current density to lower values and reduce the dendrite formation? So if you're working on a capacitor, and it's a full capacitor, it's not like a half cell here. Sounds like you're doing like a full capacitor, almost like a full battery or a full fuel cell. Um, I think what's one side is going to be has to be limiting, and so, like no matter how
Mhm.
you deal with it. So I kind of don't follow in some sense, like, well, if I increase the carbon surface area, the capacity increases. Okay, well that means that the carbon is the limiting side, because it's like if I have I don't know, I'll try to draw it conceptually here, I guess. I don't know how else to sort of think this through. But if I have cathode here, an anode here, and I have it doesn't even matter if it's a battery, it's a capacitor, it's a fuel cell, but it's like if I have this much cathode surface area, right? And I have this much anode surface area. In this case, my anode surface area is greater than the cathode. So it's like if I increase the cathode surface area, you can just think of it as like adding more material or adding more surface area, then I'll increase the capacity because it's like I have enough anode to spare or whatever. Okay, so if I keep adding cathode surface area and I add more and more, just think of everything on this side as like added surface area. Well, eventually I'm going to have more on this side, and now the cathode is greater than the anode. So it's like at some point I can keep adding surface area here and it won't increase the capacity because I've already reached the full amount of the anode, like corresponding surface area that's at the anode, right? So what I don't sort of understand fundamentally would be the idea that I increase the cathode side and I get more capacity. Then I increase the anode and I also get, like, you can only increase one of them unless they both have the same, and you can increase both commensurately. Like, you can't increase both and have it both increase the capacity of your full system. Like, one of them has to be bigger than the other just by like process of elimination, you know? So I guess I don't totally follow. To a certain extent though, the last point that you made, which is that you'll lower the current density. That is probably true. So for instance, if I, current density, let's just say J is, let's just say, I'm just make up like microamps per centimeter squared. So if I have a certain amount of current density present, but then I increase the amount of surface area, well, J will go down because this is in the denominator. It's like just mathematically, right? So yes, I think to your last question, if you increase the like zinc nanostructure and you increase its surface area, I don't know if you'll increase the capacity. That probably has more to do with which side again is more limiting. If your anode is already the side where you have more surface area, for instance, then increasing its surface area isn't going to increase the capacity because you've already like tapped out all of the cathode side. It's already all being used, right? So you add more surface area over here, the capacity won't go up, but your current density will go down because you have more area to spread the current over, so to speak. So yeah, I do think that probably is it. Whether that reduces dendrite formation, is a good question. I don't know the answer to that. I think probably the theory you might be thinking through here, which is a decent thought process, is that if your current density in general is lower, it can lead to fewer dendrites because there's lower current per area. And so at any particular spot on the electrode, there's less current, like physically, that can lead to growth of a dendrite, something like that. I don't know specifically, let's just say if, and I would say specifically for something like zinc, right, to what you're studying, if there's a direct correlation between like current, like local current density and dendrite formation. Dendrites are usually something that form, it's tricky. I know it for lithium a little better. Like with lithium ion batteries, they form at lower temperatures, for instance. They can form if you have very fast charge discharge, which I guess probably lends itself to your theory, which is to say faster charge discharge means more current, which means higher current density. So if you can decrease the current density, in theory, you would have less chance of forming dendrites. So I think you're probably onto something with that idea. I just would push back slightly on the idea of, again, for instance, does the idea of increasing the capacity on both sides, like one of them probably lets you do that. You can't sort of just increase both sides forever. They have to, like, one has to be limiting. But based on the logic of what I just talked through and what, based on your question, it does seem logical that if you increase the surface area, you would, in theory, decrease. But there's other things that can happen with that. For instance, and again, it's a little more specific to lithium ion, but I don't know if it's the same with zinc, but you have things like the SEI in films that if you increase the surface area, maybe you decrease the current density and decrease the likelihood of dendrite formation, but you might increase the thickness of your SEI because a greater surface area can increase film formation. You have more surface for which the film can form. If it's more heterogeneous, it could grow unevenly. And then it's possible if you have like secondary storage mechanisms or other kinds of things, if the SEI gets too thick, it could go the other direction. If the SEI gets too thick and penetrates the membrane or something, you could lead to a short and the formation of a dendrite or other kinds of things. The SEI is a very tricky phenomenon. Now, I don't know if that plays exactly the same role in a zinc battery as it does with a lithium battery, for instance. So perhaps not, and maybe this isn't an issue, but those are just some of the things that I can think about.
We did get a comment back. Tharia did say that she's using CH Instruments software for the thing. I've used CH Instruments software before when I was in graduate school, but it's been a long time. I just remember it was very simple. You just typed in the parameters, hit go, and then did the experiment. That was it. I guess the only other thing to do is I would actually change your parameters around. Like just try to do one cycle or to get one segment. And then with one segment, do 2 cycles or 3 cycles and then change the segments. And then see if you're getting kind of weird numbers or weird, is it consistent or did you find some just weird glitch with the parameters that they used? But we probably won't be able to provide too much support if you tell the potentious that do one thing and it does something totally different or not what you expected. And I think we'd also have to see what the data looks like. That may also give us some important information as well. So sorry.
Yeah, but it does sound like a software problem. So, I mean, you might have to contact CHI or someone who knows their software or something like that to iron out the details if it's a software bug.
Yeah. We have a question from physics tutor. That's right, physics tutor.
I used to spell physics. I used to spell physics that way. It's funny.
It is funny. It's good. It's clever.
Physics.
After changing the value of the current in GCD, I find that changing in open circuit potential. What's the reason?
Well, if you
change the current, you've done something to your system. You've added electrons or changed the voltage between your two things.
I mean, are you asking about like the end? If you're doing a galvanostatic charge discharge, the open circuit potential is constantly changing as you're charging or discharging. If it seems like the question is something like, if I charge up at some particular rate and I charge up and then down, and then I release the battery, it's at some potential. And then if I charge up like really fast up and down, for instance, and then I release it, I'll have a different like resting open circuit. And that's a normal sort of behavior. The reason for that, I think, has to do with the IR drop. So for instance, if you have a battery, let's see if I can draw this. Probably not very well. My artistic ability is not great, but I will do my best.
So very good.
That's very kind of you. Yeah. But every time I draw a CV, I feel like maybe I draw battery stuff better, but my CVs aren't so good. So let's just say I have a battery and I'm doing charged GCD, and this is voltage. So this is like V upper, and this is V lower, whatever it is, right? Let's say I'm stuck at this V lower and I'm going to do like C over 5. Okay. If this is my OCP, as soon as I start applying, it's going to like, there's some like change in the potential. And so I do my charge and it does that. And then I do my discharge at C over 5, and C over 5 is relatively slow. And so I do this. And then when I release OCP, it's going to sort of recover a little bit, and it will be like maybe ever so slightly higher than V low or whatever. Now let's say I do a different experiment and I charge at 5C. I charge a lot faster. Well, it's going to take a lot less time. And the capacity will probably suffer a little, but I might get like something like this. Okay. And then when I release, I'll probably have a slightly higher OCP. So I'm just drawing them next to each other so you can see. Don't worry about the length of the line. So like this would be the OCP that I would get when I'm done with my GCD from a faster current. And that's because I think it has to do, you can read about this in papers, and it's another one of these things I think it feels like nobody is 100% sure or explains it perfectly well, something like that. But when you start applying a current galvanostatically to a battery, its voltage jumps by some amount. And that is like the ohmic resistance or something intrinsically of the battery. So for instance, at some current, I get a voltage bump of whatever. And if I increase that current that I use, like a faster rate, then the bump of my voltage also gets higher. So what it means is that on the way up or on the way down, whenever I hit my target voltage, it's going to hit there a little bit faster if the current is higher. And then it means I'll have it's an IR drop. So the current times the resistance of the battery, whatever that is, gives you however many millivolts or microvolts or whatever the number is of voltage that is I don't know, lost or eaten up by the IR drop of the battery itself. So the OCP will sort of recover to a different value after you've finished applying the current, depending on how high the current was. And it's related to this IR drop. It's because the IR drop is leading to an artificially like higher or lower voltage in the GCD experiment itself. I'm trying to think if there's a better way to describe that. It's a hard thing to visualize, especially drawing.
Wait, why the addition of an IR drop is changing the open circuit potential?
Well, it's not that it changes the open circuit potential. It's that like, okay, so if I'm applying 1 milliamp until I get to 4 volts, okay, I'm applying 1 milliamp until I get to 4 volts, and then it hits 4 volts and it's done. It releases. Well, when it hits 4 volts, if the let's just pick a number that makes sense. If I have 10 ohms, I'm applying 1 milliamp and I have 10 ohms of resistance. Okay. Then I have I times R is 10 millivolts, right? 1 milliamp times 10 ohms is 10 millivolts. So what that means is that the actual voltage of my battery, for example, is about 3.99, not 4. When it hits 4, because 10 millivolts is like is lost in the IR drop. So in theory, if that was all perfect numbers or whatever, it would hit 4 volts, what my potentiostat says, for instance, and then it would, as soon as it opens, it would drop to 3.99, and that's where it would steady out, right? Now, if that same experiment, right, I have 10 ohms of resistance. If I'm applying 10 milliamps instead of 1 milliamp, what happens? That means my IR drop is 100 millivolts now. It's 10 times 10. So now when I hit 4 volts on the potentiostat, I've actually got 3.90. I've got 3.9. I've lost 100 millivolts. So when it decays back down after it releases, in other words, it looks like I hit 4 volts, but I didn't, because the IR drop eats it up. That's why it's hard to visualize. It's like on the potentiostat, both of those situations at different currents, it looks like I've hit 4 volts, but I haven't.
Yeah.
Because you can't really IR correct, because that's still 4 volts that is there. So you don't want to apply more because you'll over oxidize the electrolyte. You don't want to overcompensate in a battery. It's dangerous.
Yeah.
That's why the way that batteries are done to try to eliminate that is you charge up very slowly. And that's a hard thing because then it takes forever. So we try to do
Yeah.
it fast. This is like the whole battery research in a nutshell. Right?
Yeah.
It's like when we charge up really fast, we lose a lot more to IR drop. We don't actually get up and down where we're trying to go.
That's the title of this video now. Battery research in a nutshell.
Battery research in a nutshell. Exactly. So that's how I can kind of describe that. Let's see. I have a huge IR drop also in EIS. The electrode resistance shows 40 to 80 ohms. That's huge for a battery. How can you reduce that? Build your battery better. I'm assuming
get better.
Get better.
I'm joking,
bro. No, I'm just kidding.
Yeah.
So typically batteries are sub 1 ohm, at least sub 5 ohms. Sometimes it's milliohms range of impedance. Increase your electrolyte concentration. Make sure the electrodes are pressed together as much as possible. That's why we use coin cells or cylindrical cells where they're wound very tightly, or there's a compression disc where they push together really, really tightly. That reduces the impedance. And it's one of the reasons why batteries are built the way they are, because they use non-aqueous electrolyte most of the time, right? With like lithium ion. And those lend themselves to high impedance. So when everything is really close together and pressed together, you reduce the impedance by a large amount. Everything's pressed into a membrane of the separators as thin as possible, electrolyte concentrations as high as possible. Those are some of the things you can try to do, I guess. Look at the battery construction most of the time. This is probably a situation of less about
like the chemistry of the battery.
Exactly. Less about the chemistry of the battery and more about engineering and physical physical conditions, right? You'll probably be able to dramatically increase your impedance and improve your results by tinkering with the physical configurations of things, working with a supercapacitor. So it might be the same with a supercapacitor in a similar way. So it's maybe it's not a battery, but there's similar phenomenon as far as the construction works and all of that kind of stuff. So that if you're working with a supercapacitor, perhaps that's not as high, but or use lower currents, right? Lower currents will reduce the IR drop. But of course, if you have a high amount of resistance, it's going to be tricky.
Okay.
Where were we?
Let's figure out where we were.
See. Okay. A lot of back and forth here.
Yeah. Let's see. FCB is talking to Chris a little bit about how do I confirm my ligand is not stable in the applied potential range in CV? Usually, if you do cyclic voltammetry and then you do it again, it's not it comes off, or you have an irreversible scan. Sometimes truly what inorganic chemists do to determine whether or not their ligand is coming off is they actually have to do NMR. They have to do another analysis of something. They have to do like bulk electrolysis of their system to see how stable their their inorganic complex is. And then they do NMR, and then they see when it's like one of the solvent molecules replaces the ligand, you have a different molecule. Also, you may observe a shift in your potential for the metal ion or the metal complex because it's a different complex. So that's one way to determine. Those are the signs you want to look for, whether or not you have the ligand is coming off your system. So that's at least a quick answer to your question. And I guess just kind of moving down because it looks like we have a lot of comments, but I sometimes don't know whether or not it's a real question or not. Give me a second to find. We have a question from Jenny. During EIS measurements, I observed a semicircle in the Nyquist plot that starts near the origin with a resistance of approximately 200 ohms per square centimeter. And then Jenny continues, however, at lower frequencies, I noticed that part of the semicircle extends into the negative impedance region. What is the physical interpretation or significance of these values, significance of these negative impedance values? And then she goes on to further clarify Negative values in the real part, z prime, meaning the semicircle crosses into the left quadrant of the Nyquist plot.
I think you must mean at higher frequencies, not lower frequencies. It does not seem feasible that at lower frequencies the semicircle goes into the negative region. Let me reread this. During EIS experiments, semicircle starts near the origin with a resistance of 200 ohms centimeters squared. Okay. At lower frequencies, I noticed part of the semicircle extends. So, in general, the answer to your question is that it's either an artifact or it's a reference electrode problem. Artifact is sort of a general term used for any error that you might observe. Often it has to do with the reference electrode, and sometimes it has to do with just the potentiostat itself and cabling and wires. And so it's sort of like stuff out of your control. So it's not anything you did, or it's not anything sort of wrong, so to speak. It's just an intrinsic property, right? If it's related to the reference electrode, it either means you need to decrease the frequency you're using, check that your reference electrode is not blocked or has an unusually high impedance, or use a shunt. But I think your description is something is I'm misunderstanding about your description. For instance,
unless of course she's getting like those Death Star looking things from your webinar that was 2 days ago on Wednesday. If you're not aware, Neil is doing an EIS webinar series, and Jenny may actually have attended that maybe. But you should absolutely check it out.
So what you've described, for instance, if I have Z real and Z imaginary, and this is the origin right here, right? 0. So I'm just reading what you've described. Let me see if you've made any. So you say, during EIS measurements, I observed a semicircle that starts near the origin with a resistance of approximately whatever it is. Okay.
200.
Yeah. The exact number is not real. So here's near the origin.
Yeah.
Here's a semicircle. So this is the start of your question, just to think it through, right? At lower frequencies, okay, lower frequencies are over here. This is lower frequencies. Part of the semicircle extends into the negative impedance region. So what you have described quite literally to me is that over here, this is lower frequencies. It extends so that way over, like, this doesn't make any sense. So I think I'm misunderstanding you, perhaps, or you mean at lower potentials, or you mean at higher frequencies. So perhaps you mean something like you actually have something like this, like your semicircle starts in the negative Z real, or like it will, if it extended all the way, sometimes you get something that's like this. Like if it extended, it would extend into the negative, something like that at the higher frequencies. Or you mean what Alex was referring to, which is his favorite topic, which is an inductive loop, which you did clarify you meant the negative Z real. So I don't think this is exactly what you mean, but sometimes you have a loop like this. In an extreme case, you might get something that's like really curling. Like, is it doing something like that? I mean, that's ridiculous. I don't know if that's exactly what you mean, if it's curling that far back. I kind of want to know, is it one of these red curves? Is it the blue curve? Is it,
so Jenny says yes, like the red one, but red one, I guess, on the second page.
Probably the first,
by the
first page.
By the first page.
It's probably like this, like this right here, where it extends into the negative. If you were to I think I understand what you mean, Jen. Let me come back to it here. So like the red one. Yeah. So I can probably illustrate this in our software. So I had another webinar some time ago. I'm going to try to pull it up here, but I showed how with a shunt you could rectify this kind of situation. Advanced circuit fitting.
First one.
And where was it? Was it with the code? No. Where did I talk about this? Shunt. I'll find it, I promise. I talked about a shunt with respect to reference electrode shunt, coated steel corrosion. This one, maybe. Okay, I'm pulling up some data. I'll try to show you now. All right, let's see. So shunt examples. So no shunt. I'm guessing you saw something like this. So hopefully you can see, here's a Nyquist plot, but look at where 0 is. So it's like, hey, look, as I go into the negative area here, a negative Z real or whatever. So this is not a real thing. In other words, there's no such thing as negative real impedance. Like, it doesn't make any sense. It's like a energy creating problem. So what I did was I add a shunt, which is a separate pathway for the reference electrode at high frequencies, because at high frequencies, there's a phenomenon where the reference electrode cannot keep up with the potentiostat's speed. And so its potential is not accurate, essentially. So I use a capacitor that bypasses the reference electrode at high frequencies. And the shunt comparison, you can see here, for instance, with using a shunt and not using a shunt is the black to the red. So what I did was I used the shunt and I was able to take the black curve to the red curve. So after a while, they are mostly the same. They mostly line up. But I was able to fix this problem because in other words, it's not your system. It's nothing about your system. It's the potentiostat issue and a reference electrode issue. You can see in the Bode plot for the first, in this particular case, it was like 1.5 decades from a megahertz to about, I don't know, 20, 30 kilohertz. These two plots here, like these two don't line up, and then they line up, and then it's about the same. And basically that means that the reference electrode was not doing its job for all of these points. So I used a shunt and helped kind of fix that problem. So I guess I'm going to just sort of remind myself exactly like that. Yeah. Was the question, what does it mean? Like, what is the physical interpretation? Okay. I'll talk through the physical interpretation. You did ask what it is. So, it is what I would call glass capacitance. It's a very weird phenomenon. I'll explain it. So, what you have here at these frequencies, when this occurs in solution, I have, my reference electrode. I'm going to draw it really big and only the reference electrode just to illustrate this for you. Okay. So here's my reference electrode. Typically we have like a frit. We have a wire, like a silver wire. There's a fly around me. It's back. Right. It was around me in my webinar and I wanted to get it and I couldn't get it. All right. Sorry. Getting distracted by a fly. All right. So in here I have something like KCl, right? With an AgCl wire, whatever. It's my reference electrode. And in the main solution, I have my electrolyte. All right. Now, when the potentiostat is measuring impedance at high frequencies, it's contending with this frit, okay? So this frit right here, Z frit, might have an impedance of, let's say it's a bad one. It's kind of blocked. Let's say it's 10 kilo ohms. That's bad. That's usually pretty bad. That's on the high end of a reference electrode. Sometimes double junction can have kind of high or whatever, but let's just say it's that. Okay. The potentiostat is measuring effectively a pathway from the reference line, right, of the potentiostat through this wire. Let me draw a different color, green. Right, it's measuring through this wire. Now there's almost no impedance. It's a wire. It's like a metal wire, and silver is the most conductive metal on Earth, so there's no impedance. Then it has to make its way through the solution. Not too bad. It's a highly concentrated salt solution. And then it has to make its way through the frit, which has 10 kilo ohms. So most of all of this pathway up here is like, let's just say like 10 milliohms. It's almost nothing, right? So there's almost no impedance whatsoever. So all the impedance of the reference electrode is basically contained within this frit at the bottom. And that's to make sure that we don't have too much crossover between the inner fill solution and the main electrolyte. We're trying to avoid contamination. So the impedance of the frit is 10 kilo ohms. Now, the the reference potential that it's measuring will go on that pathway unless there is a pathway of less impedance. And it just so happens that most reference electrodes are a glass, right? It's a glass tube. Okay. And there is liquid on this side, and there's glass right here. That is a capacitor, technically speaking. Now, the dielectric of glass is very bad. It's not high, right? Let me look it up. Dielectric of glass. It's like super small, I think. Yeah, 3, 4. Okay, it's a low number, right? The point is, though, that it does actually exist. So you can have a capacitor exist on either side, and it just so happens, if you do the math out, okay, there's solution on this side, and there's a glass. If you calculate roughly the surface area, basically, of the glass that's in solution, depending on the average size of your reference electrode, of course, it'll depend. And the dielectric of glass and the typical thickness of glass, maybe it's 1 millimeter, maybe it's 2 millimeter. The capacitance of my reference electrode glass might be about 10 picofarads, 7 picofarads, something like that. Okay. Now, the impedance, let's go to our software here. The impedance of a 10 picofarad capacitor. Well, what is that? Right? Let's show you. I'm just going to get a capacitor for you. I know you can't see me drawing this, but I'm doing it anyway. I'm getting a pure capacitor. Okay.
Yeah, it just looks like you're moving your mouse around randomly. But
I am.
But we know.
I am just moving mouse around. Yeah. Okay. All right. So let's get 10 picofarad capacitor. Right. Simulate. All right. So here's what you can see. Hopefully, I'm gonna duplicate this plot. This is the Bode plot. That's the only one that really matters. This is the Bode plot. This is the impedance frequency plot of a 10 picofarad capacitor. So capacitance, let's say, is providing a impedance that's lower. And in fact, it probably is a lower capacitor gives you a higher, it depends on the value of the capacitance, how much glass, the thickness of the glass, all these things. At any point in any frequency, if the impedance of my capacitor, of my glass, is lower than the reference electrode frit, that is where it will try to measure. And basically, the long and short of this is that the potentiostat can't measure the potential through the glass. Like, it's, of course, it acts like a capacitor, but it's actually not penetrable, right? There's no measurement directly, like there's no real measurement through the glass. So that's why you get this error, basically, is it can't really properly measure the potential between the reference and the main solution. And so you get this error until the frequency drops such that the impedance of the glass basically becomes high enough that it can't measure that, and it measures through the frit. So that's sort of the phenomenon that we're observing here. And I do see that, yeah, the audio cut for a bit. and then hopefully it's back. I don't know.
Yeah,
Weird things are happening.
It was very short when Chris
Okay, yeah, when I'm
typed
moving
that
an
in,
axis,
that's fine.
it cut out for a second. So
yeah,
super fun. But hopefully you caught most of the point here, Jen. Is it's this glass capacitance phenomenon. It's a very weird thing, and it's one of the reasons why sometimes the advice that I have for people who have this problem is dip your reference electrode as little as possible into solution, because what that does is it decreases the glass capacitance, which increases its impedance, which makes it less likely to bypass the frit. So barely dip the reference electrode in solution, like just the frit. You don't have to have the reference electrode dipped all the way down, because that increases the capacitance, which decreases the impedance, and it makes it more likely to have an artifact by a little bit.
Yeah. All right. It's very good. Okay, we got all right, so moving on, we have a question from Sudeep. Sudeep asks, how would the Nyquist plot look like when you have a capacitor and inductor connected in parallel and then series? So while you're answering that question, I just figured I would circuit fit, and I would try to make something like that.
How did you do it?
So it looks like this. The Nyquist plot is a straight line because you only said an inductor and a capacitor in parallel and series.
Wait.
So this is the circuit. There's no resistors in here. So
capacitor and an inductor in parallel, and then I don't know if he means what you've drawn, which is ridiculous.
this is exactly what he asked.
Or he means like one or the other. I don't know if he means one.
Oh, one or the other.
Yeah, like
I think they'd still. Well, here's the interesting thing. I think they both kind of they'd be similar because
they have no resistive element at all.
they have. Yeah, I have no resistive.
It's just going to be something that alternates between positive and negative 90 degrees.
Yeah,
because capacitors are minus 90, inductors are plus 90, and you have no resistive element, so you will have no real component to the impedance whatsoever, and this is just a wonky system.
And I bet Chris is really happy, because I bet this describes like a very specific like electronic circuit.
Probably a transistor, right?
Yeah,
transistor type thing, which is like or whatever. It's like all one direction or all the other direction or something.
Yeah.
Chris, is that something that you see?
Maybe he's very
oscillator. Yeah, it's an oscillation thing.
Yeah.
But it's also not realistic, because nothing has even a capacitor, like a pure plain capacitor you buy from like DigiKey, has resistance.
Yeah,
to it. Like it has some there's no such thing as zero resistance. So this is a fun simulation that you can do in our software, for instance, and look at a pure inductor and capacitor and whatever.
Yeah.
But yeah, resistance. There has to be some resistance, but it's kind of a fun RLC tank circuit. Interesting.
Yeah.
Yeah, that's kind of fun.
Okay. Interesting. Well,
so yeah. Well, anyway, it looks goofy is the answer to your question. Yeah. But yeah, this is why software like this is kind of useful. You can kind of simulate all these things and see what they look like if you're just curious.
Yeah.
So yeah, it's a good question. What do they look like? Put them in software.
Put them in and check it out
and see what it looks like. Yeah, that's funny.
All right. Let's see
here.
Was there another?
I think Javid had a question. But how do we calculate density of states from EIS data? Density of states.
Density of states. I don't know. I don't know if I'm sure maybe there is a. It's been a long time since I've looked up density of states. That's like
a physics thing.
It's a physics thing. It's like a.
I don't know much about.
It's like a statistical mechanics thing.
Phase transition thing. Is that it's a phase? I'm just looking it up quickly here.
I never thought of it. It's like density of states number.
States of what? Like what is it related to? Because I obviously know about impedance. I'm trying to think how you would make that connection.
Yeah, states are always.
If I can,
density of states I don't know what system describes the number of allowed modes or states per energy range. I don't think EIS.
There might be a way to do it.
There might be a way to do it.
Like maybe the resistance that you get from impedance can be used in a density of states calculation of some kind, but I don't know. Because I don't know enough about density of states as a thing. If this is a physics concept, I don't know that I've ever learned about it. Or studied it, to be honest. Density of states.
Was it? Chris said model it in P-Spice for bonus points.
Why don't you model it for bonus points, Chris? I'm not in school anymore. Yeah, that's a good
Yeah.
question. Honestly, I don't know. I feel like there might be a possibility where that could be done, Javid, to be honest, but because impedance allows you to probe stuff like resistances and capacitances, inductances, right? Which are electronic physical properties or phenomena, I guess. And so it's at least conceivable that something like that could have a sort of crossover, if you will.
Yeah, I
But
mean, you kind of use EIS with Mott Schottky because you determine the electron donor density, which is kind of an indication. Yeah, so I'm briefly reading through it. There is a section on looking at density of states of electrons at the band edge between the valence and conduction bands and the semiconductor. For an electron in the conductor, an increase in the electron energy makes there more states to be occupied. Alternatively, density of states is discontinuous for an interval of energy, which means that no states are available for electrons to occupy within the band gap of the material, right? There's no place for an electron to go in the band gap. And so, yeah, Mott Schottky has some of this, usually used for semiconductors. I don't know if it has.
I don't think Mott Schottky will work if it's not a semiconductor because you need a space charge region.
Yeah, that's right.
And
yeah.
a conductor does not have a space charge region.
Yes, the conductor does not have a space charge
It's
region.
it's too conductive.
It has a very large density of states.
See what you
it
did
has
there.
a lot of it has a lot of electrons. It can't.
Yeah.
So
yeah.
sorry, Javid, we're just kind of rambling about ideas, but
talking
I don't
it through.
know.
Yeah. The reality is, I think there's probably some crossover there, but I don't know the answer.
Yeah.
Let's try to get to the questions we had saved because now we have a chance to get through this questions. Please ask questions if there are some live. We've had a couple saved from last week and from I think a YouTube comment as well. And we wanted to get to the live questions first, but feel free to ask some questions. We can hang for a little while longer here, but we'll get to these questions. This question was asked, I think, right towards the end of last week's live stream by Arthur. And he asked, is there a way to determine an equivalent circuit for Nyquist diagrams numerically? So the answer is probably, but the reality is circuit fitting with a circuit analog is the far more common way to do that. And the only benefit I can think to fitting like a Nyquist plot, really, it's not necessarily just a Nyquist plot. If you're focusing on just the Nyquist plot itself, I guess that's fine. You could think about a Nyquist plot in the same way you'd think about any data on a Cartesian plot fitting XY data, right? You can fit it to like a nth order polynomial and like fit data, right? So you could basically numerically fit almost anything. The positives and there's positives and negatives of that. For instance, you could get an empirical kind of analysis of a Nyquist plot that looks a certain way by fitting it to some equation numerically. Whether that is meaningful and at all, though, is the negative because, very likely if you fit an empirical numerical relationship to a Nyquist plot or any impedance data, you're just fitting some arbitrary equation to your data. Now that again can be used in an empirical way to predict future behavior. Like I see this impedance plot later, and assuming the conditions are the same or similar, I can use my numerical fit to say, well, that means this conclusion about my system. So there are practical uses for that. The problem, of course, is the lack of meaning, right? So when you do a circuit fit, you are both numerically and qualitatively fitting your data. And so there's more value to that. So for instance, if you fit a resistor and a capacitor and a CPE and an inductor or whatever you're fitting to your system, you get a numerical solution as well. Now you don't really see, for instance, the equation in the same way because you don't need it really. But like when you fit your Randall's circuit or whatever to your data, what's actually happening is that the software, for instance, is fitting a numerical equation. It's a big, when you solve the math for a Randall's element, you get a big mathematical equation, right? So you are fitting it numerically. It's just that it's more valuable to say, well, this is the charge transfer resistance, this is the double layer capacitance, this is the Warburg impedance, and here's the values associated with those. So not only am I numerically fitting my data to get possibly empirical or quantitative analysis, I'm also getting a real representative fit of my data to say, well, this is charge transfer resistance. It's not just a number. It represents the kinetics of the Faradaic process. And so there's more value and there's power in fitting it that way if you can. So, so again, I think in some sense, yes, you can fit, Nyquist data or anything else numerically in just a pure empirical way. And unless there's a specific reason to do so to predict future behavior or something like that, a normal sort of circuit fit analysis is usually sufficient.
All right. So there's a new question from Shamim. So Shamin asked, recently I obtained EIS data for my sample drop casted on nickel foam in 0.5 molar sulfuric acid electrolyte. When do we get negative impedance values in EIS data? I don't know if you want to do this, Neil, but I might recommend Shamin watch a little bit earlier. We actually talked, Neil did a big description about why you get negative or how you get negative real impedance. So
Yeah, we're at about 1 hour and a half. It must have been somewhere around 1 hour and 10-minute mark of the video. Of course, if you're watching this video later, there's a timestamp, and so you can find in the timestamp where I answered the question from Jen about the question was, hang on, I'll find it so I can tell you now. And then probably by the time you're watching this, the timestamp is there. But it was about what is the physical interpretation or significance of negative impedance values. So again, I talked about that. And in short, it has to do with most probably negative impedance values have to do with reference electrode, stray glass capacitance, artifacts from the potentiostat or things like that. And I talked about other possibilities for the negative impedance, if you mean negative on the y-axis, for instance, that is an inductive thing or an inductive loop. That'd be something different. But if you're meaning that it's going negative on the x-axis, for instance, negative z real, I talked through that. So go back in time. YouTube allows you to travel back in time. It's a very sophisticated platform.
Yeah.
And check that out. I explained that process.
Yeah. So we have a question from Amna Murtaza. She says, kindly tell me about double layer capacitance calculated by CV in the non-Faradaic region, as well as how to calculate the double layer capacitance in the CV in that region. And I also want to relate this because we had a question earlier from George Lucas, who watched my cyclic voltammetry YouTube video, just an introduction.
He has more time on his hand because he sold Star Wars.
Yeah.
Sorry, I couldn't help myself.
So
it was right there.
Yeah,
it was right there.
I know it's right there.
I couldn't. I'm sorry. It's a cheesy joke.
And George Lucas was asking that, like, okay, when he does his test solution without the analyte, his electrolyte solution, only electrolyte, no analyte, the graph did not turn out. The CV didn't turn out like a regular cyclic voltammogram. It turned out rather like half a typical graph. He didn't see it climb back up, and so George Lucas is asking whether or not this is related to the electrolyte solution. And these questions are actually, while they may seem unrelated, they are actually both related to each other. Amna's question and George Lucas's question. So to kind of talk about this, in my cyclic voltammetry video, I described that when you do not have an analyte in your electrochemical system and you do cyclic voltammetry, you tend to get a voltammogram that looks a little bit like this, and it kind of jumps up. You have it kind of looks rectangular, and usually there's some edges as you move, right? And so this is like 0, This is a zero current. And this current here is the non-Faradaic capacitive current. So I can't draw very well, or I can't type non-Faradaic farad current, right? So if you actually just measured this, and there's a scan rate, so this should hopefully help answer Amna's question. The current associated with a double layer capacitance, the current is equal to the capacitance times the scan rate, which is represented as dV dt. And this comes out from just a capacitor. The charge on the capacitor is equal to the capacitance times the voltage. And if you take the time derivative of this expression, you get this expression. So a great way to determine what the capacitance is in the non-Faradaic region is actually to do a series of scan rate. I'm just drawing these kind of haphazardly, if you will. A series of scan rates, and you should be able to plot the scan rate dV dt versus current. And as you increase the scan rate, you should get a straight line with different data points. And there should be a linear relationship between these two. And that linear relationship, you should just be able to do a linear regression, and the slope will be equal to the capacitance. That's all it is. And it works pretty well. I've actually done this with certain systems. So to George Lucas's point, make sure that when you're doing cyclic voltammetry, you do a cycle. So in your applied potential, let me get rid of this. So in your applied potential in cyclic voltammetry, this is what the applied signal looks like. You have your voltage over time. Instead, you usually apply something that looks like this. From the way you described it, George Lucas, you only did this. You only applied one of these. You didn't complete the cycle. And when you do that, you're only going to get a flat line. And yeah, maybe there's a zero current. And you could still use that value to determine what your capacitance is. But it doesn't necessarily mean that your electrolyte has gone bad, per se. All right. So I don't think you need to do that. Now, one, I guess, last thing regarding this. Let me just make sure I double check the questions to make sure I'm answering all the parts. So that's how you calculate from the non-region. I think there was one more point. Is there one more point I was going to try to make? Oh, right. So when you are doing, when you're doing this, you're probably not just going to have blank electrolyte. You may actually have, a voltammogram. I think it's important that you are able to recognize that, like, you should be doing that experiment in this region. You should do it where there is no Faradaic processes. You do not want to convolute Faradaic processes with your non-Faradaic double layer charging that's going on in here. So just make sure, like, if you're doing like a full cyclic voltammetry sweep, you only scan between this range, because actually I think I made that bar a little odd, but that's okay. You want to just make sure that you're only scanning in this range, because let's just scan within this range for the voltage versus current. Because in this part over here, you still have a lot of redox species occurring. So if you only scan within this small range, you're not gonna generate any redox species on either side of the reaction, whether it's the oxidation or the reduction. So only scan within here. Don't scan all the way and back, because this current here will have contributions of Faradaic processes occurring on it. So if you used both of these, like this part and this part, you may have some inaccuracies when you're measuring the double layer charging the capacitive current. So hopefully that was helpful, Amna. Let's see. Amna has another.
Yeah, this is a bit of a. I think there's a misunderstanding here.
Can you please tell me when we plot a graph between peak current versus scan rate, why we divide the value of the slope by 2 to get
CDL.
CDL value?
I don't think you get the double layer capacitance from a plot of peak current versus scan rate. Are you confusing this with
Correct.
diffusion coefficient or something? So
Yeah.
when you plot peak current and scan rate, you normally plot peak current versus the square root of the scan rate. First of all, if you look at, we have our handy.
Oh, yeah.
Where is it? Is it in design in here?
Yeah, it should be overlay.
Where is it? There it is.
You got it.
There it is. Randall-Sevcik equation. Look at that. So, yeah, sorry, you got the question. So in the Randall-Sevcik equation, for instance, the peak current is proportional to the square root of the scan rate. There's no capacitance term in here. And in fact, when you're looking at a peak current, fundamentally, you're looking at a Faradaic process. Compare that to a CDL is a non-Faradaic process. So there's a bit of, in my, I don't know, estimation of your question, misunderstanding about trying to get capacitance from a peak. I think you might have a slight misapprehension here, or please clarify, like which equation are you using, or why are you? I mean, maybe are you confusing like dividing by 2 with taking the square root, friends? Like, you know what I mean?
Yeah, and
I don't know.
Sometimes you divide by 2 only if the current is the total current of both.
Oh, maybe that's
bands.
what she means.
Yeah, so only
that makes more sense.
But there's still no peak.
No, it's not a peak, but maybe the word peak, she just means like the
top,
the levels. Yeah. So, well, you just drew it, right? But
yeah,
but the reality of that is what Alex drew. I think you drew mostly that. But when you have your CV, again, it's not a peak, but this might be a difference in terminology here. When you scan positively, that's the current, that's the charging current, and then when you scan negatively, it goes that way, right? And so this is the current the other way. So the current is, if you take the current as this here, right? This is 2I. Like this, the whole band is twice the current, because the current that we're talking about, that is with respect to the charging of the double layer, is from 0 on it's 1/2 of the band. So that, I don't know if that's what you're asking. Again, it's not a peak, but I think that's what you mean by peak, perhaps. So, because that's the current of interest. From 0, when you're not doing anything, as soon as you polarize the electrode, you set up the double layer, and there's a current associated with that in either direction, right? And so it's not the full band. It's from 0 to whatever place. So if you're taking the full band, you have to cut it in half. I hope that's clear, and I hope that's an answer to your question. I think that's what you meant.
Yeah.
So,
yeah.
Looks like Akashdeep has a question about capacitance. So capacitance from EIS should always be smaller than capacitance calculated from CV. I don't believe that's true. Is there any specific relationship? Well, to a certain extent, they are different methods to calculate, in theory, the same thing. I think the tricky part, of course, is that, and you know, as an analog, for instance, I have talked about in my webinars about, you can calculate the diffusion coefficient, for instance, from something like Levitch sweep techniques, and what, you know, rotating experiments. And then you can also calculate it from impedance. And when you do that, they don't always exactly get the same number for your diffusion coefficient, right? And it's like, well, what gives? Which one's more accurate, right? It's a tricky thing to answer. You know, to this day, I don't know that I have a perfect answer to this. I tend to follow the perhaps unsatisfying, but it's the only honest answer I can think to give, which is that there's generally value in doing all of the above methods to give you more like diversity of value or something like that. Like, do CV, do impedance, see what values you get. With impedance, I think it's trickier, maybe only because like you're at the mercy of how well the circuit fit works. Um,
Hmm.
with CV, it's a little more straightforward, I guess I'd say. Like the current is what it is,
Hmm.
right? Whereas with impedance, it depends on how well you've picked your circuit. Is it just a capacitor and a resistor in series? Is there a semicircle at all? Do you have anything Faradaic? Do you have a film, substrate film?
Mm.
Did you go to enough frequency ranges? Is it did Kramer's Kronig show that it's like legit data? There's a lot of other sort of ancillary questions that make it a little harder, I think, for impedance. I don't like to trash on impedance. I teach impedance a lot, but in some cases, I do tend to fall in the lines that maybe CV is a little bit of a more, I don't know, consistent pathway towards getting this kind of capacitance. I tend to
Yeah.
feel that way. I don't know if that's accurate or not, but
Yeah,
I do the same with
don't know.
Levitch. Like I feel in general like the Levitch approach is a little more rigorous for getting the diffusion coefficient than the Warburg, just for whatever reason. And I just, some of it's in my own experience. It just feels a little more accurate. I don't know.
Yeah, one thing about some of the techniques. So, for example, like that, actually, the thing I like about impedance in principle for calculating the capacitance is that it has to do with kind of how much are you sampling the like the thing that makes Levitch give you a really good calculation of the diffusion coefficient is you have a steady state current, which means like you really know what that current value is. It's like really, really well known. You've measured it very well. In CV, it's a transient response. It's just at the moment the potential's at a certain point, we collect a current. If we collected it here, it would be this value. If we collected it here, it would be that value. But and we're talking about really, really tiny differences. But there are differences. But with EIS, you could take 1 million samples, in 1 second at
and the
1
exact
megahertz.
current is irrelevant.
Yeah. So, and so like you have, if the quality, again, to Neil's point, if the quality of the EIS data is very, very good, which in principle it should be because you're measuring something several, like lots and lots of times to really know what that value is, then I usually think, oh, maybe it's good.
Yeah.
I wasn't going to trigger you, but you could also look up the chi-squared value to see how good your EIS fit is, to know how well your capacitance.
You're gonna make me just get up and leave. You could check the chi-squared
value.
Chi-squared. Did you just say? Man, I forget what we did for that one. Was it that guy I cared or something? I can't remember.
I have to remember.
This is super inside baseball in one of our podcasts.
Yeah,
I don't even know which episode we put that ad in.
I think that was the last one.
Oh, because it was our trigger things. Yeah, it must have been the last one. Yeah.
Yeah.
I can't remember.
I can't remember that.
Damn. It's like, I shared. It was
I shared.
Yeah. Like, hey, you want some chocolate? I shared. Chi-squared.
Hey, what are you talking
about? Nobody
about?
knows what we're talking about right now, but I don't care. It's funny.
But anyway, they should be the same. Ideally, they should be the same within. Yeah. And if it's an order of magnitude, like if you measure 1 versus 10 microfarads, okay, that's a big difference. But even if you measure 1 or 2 microfarads, that's actually still pretty close.
Yeah, I think it's getting all the data and seeing, over different days, over different experimental conditions, see which one seems to be more consistent. That might sort of direct you to which one you want to trust more. To Alex's point as well, it's like there might be a situation where you're having trouble in the other way, which is that CV or like a diffusion limiting current or something, whatever, maybe it doesn't flatten out very well and CV is looking more poor. Impedance is a way to get a lot of data really nicely. Maybe it's more stable. Maybe your chi-squared values are good. Maybe your Kramer's Kronig looks good. And maybe EIS is something you could trust more. So I just sort of generally, like I said, try to recommend get all the data and more data is helpful. You can always sort of discard later perhaps what appears to be less accurate or something like that, but you won't probably hurt yourself by getting more and being more thorough, I guess.
And he does have a follow-up, if you want to just look at this quickly. He says also, if EIS starts in negative value, should we consider the L component,
Yeah, the inductance.
Yeah, the inductance.
You can, but it really does not matter. It's not important. So if you have, for instance, what I'll show you now here. If you have, for instance, and again, I'll just bring up a circuit. Give me a moment here. That one. Okay. If you have a plot that's like this, where the inductor, it starts out with a negative kind of thing, you can fit a leading inductor and get the inductance value. The issue mainly is that nobody cares what that value is. Nobody cares. You shouldn't care. The reviewers won't care. The readers won't care. Nobody cares because inductors are irrelevant. So just as easily, you can basically start your data here and be like, hey, look, there's no inductance. Now you're not lying. You can show it. And I guess if you're trying to be like complete or something, you can fit an inductor and just sort of put its value in a table, in your paper. Like, here's the values we fit for our Randalls or whatever. And we have an inductor value, but like nobody cares. It doesn't, when you have this kind of inductive behavior at high frequency, it's just cabling or whatever else. Like it's not relevant. Almost never. It's almost never really needed for the analysis of your system. So you can just kind of fit it if you want. Otherwise, you can literally just like ignore it, pretend it's not there, and just fit the positive data that this is where what's happening of interest, like charge transfer processes. So that's what I have to say about that. Yeah. If you want to, go ahead, but you're not going to hurt yourself by sort of just hand waving in a way. It's not that relevant to the other parts. And part of that reason is that it usually happens at high frequency when nothing else of interest is happening except IR drop. And it doesn't usually impede your ability to measure the uncompensated resistance because you still have an intercept at the Nyquist plot high frequency. So the inductance is just there. And then by the time you get to what matters, the inductance isn't influencing your measurements anymore.
Yeah.
So
there was we're running out of time soon, but there was a question by influential Tishepo, says, is this suitable for UK, I think grade school 12
or grade 12?
Grade 12. Probably not. I think this stuff's a little bit advanced. Not to say they can't try, but a lot of the material and stuff, electrochemistry is really you learn it usually in graduate school. So after you have a college degree in engineering or the chemical sciences, that's usually where people start to pick this kind of stuff up. There's a lot of stuff. It's pretty advanced.
In my entire career, I think I can count on one hand the number of high school students or high schools I have ever interacted with who have any interest or sort of, project or whatever going on with electrochemistry. It is just generally speaking a secondary education subject. It just lends itself to a little bit of a higher educational barrier, I guess. So
there's just a lot of content that needs to get covered before.
You have to know a lot of other things, right? That undergird your study of electrochemistry, I think.
I think there's one more question from Antonio. I think this might be the last one that we take for today. Hey, do you have any tips for cleaning screen printed electrodes on polyester with graphite for the working encounter and silver colloid for the reference electrode? This kind of sounds like our screen printed electrodes.
Yeah, it does. It's not polyester.
Not polyester, but it's a type of plastic. So, I mean, my quick recommendation is that you can do cyclic voltammetry cycling in dilute sulfuric acid. Ideally, the plastic that you're using is compatible. That's the whole main thing. Are these things compatible? And so usually dilute sulfuric acid, you can have some of these things. Maybe polyester, maybe not. But if you have like a polystyrene or something, or polyethylene, a stronger plastic, you might be able to do cyclic voltammetry cycling, and then you'll just start to see you'll see these oxidation peaks in your voltammogram start to decrease over time as you clean the electrode surfaces for the working counter electrode. So that's my recommendation, because there's no way you can mechanically polish some of these screen printed electrodes. It doesn't make too much sense. But I'd look into the material just a little bit further to know what's compatible. But acid cleaning and cycling electrochemically is a great way to do it.
And, the main point is that it's not often possible to physically clean screen printed electrodes because you will wipe away the trace most of the time. So so just generally speaking, avoid physical abrasion type techniques, right? Because you would probably damage the traces. And, well, that ruins the screen printed electrode. So
yeah.
Cool. I think that's gonna do it for us this week.
Yeah.
As I always like to do, look at the calendar. I think we're good for a few weeks here until probably the Thanksgiving holiday here in the US.
Yeah.
Which is it's the last week of November, right?
Yeah.
Like
so
27, 8, 9. That
yeah,
time
27, 8, 9.
Yeah. Okay.
So yeah. So that'll be the next time that we do this. Or no, that'll be the time, so the 29th will probably be off. This is the 1st of November. Yesterday was Halloween, for those of you in the States who celebrate with kids and candy and all that stuff.
I always celebrate candy.
Always celebrate
Just
candy.
personally. So yes.
So 8th, 15th, 22nd, we'll all have live streams. And just to let you all know, next week, Wednesday the 6th, Neil will be doing a webinar on EIS, on impedance. So on the Pine Research website, you can click the link to register for the webinar. We'll also be streaming it to YouTube at the same time. But yeah, you should try to attend. It's completely free. And again, thank you all for all of your YouTube members and asking us questions and supporting the content that we generate and asking really good questions.
Yeah, we appreciate it. And just as a note, Shamim, we see your question. We're wrapped up today, unfortunately, but I'm adding it to our list. So I will answer your question first thing next week. I'm sorry you have to wait a week. But next Friday at this time, 1 p.m. Eastern time, we'll get to your question first. We definitely tried not to miss any questions, but when we reach the end, we're sort of stuck here, unfortunately. But anyway, thanks everybody. As you said, appreciate the engagement, and I hope everybody has a good rest of your day or weekend.